Okay. So chapter 5. So introduction to fluid mechanics. Okay, what is fluid mechanics? So in this chapter we will study about basic concept of fluid mechanics. So today we will learn a few terms that we will be using in the fluid mechanics. Then the type of fluid flow problems, then viscosity, tension, capillary effect. So we will cover part 1 and part 2 today. Okay, and part 3 will be tomorrow. Okay, so fluid properties. So properties are very important because when we want to do analysis related to fluid, so we need to have properties, and then once we have properties, then we will use it to do calculations. Okay, properties like velocity. So velocity is a property of fluid. Then mass. So all that will be used in your calculations. Okay, so that's why fluid properties are very important. Okay, so we will see few properties. The first one is density. So we have studied about this before. So density is defined as mass per unit volume. Okay, so mass m over volume v. So that is what we call as a density. So this we call it as a rho. Okay, so in 1 unit volume, so how much mass you can put? So that is how density is defined. Then we have a specific gravity or relative density. So this is a density also, but it is based on relative. Relative means is a relation with something. We always write as Sg, stands for specific gravity. So if we recall from the previous chapters, specific gravity is defined as the ratio of the density of a substance to the density of a standard substance at the specified temperatures. Usually we will compare it with water. Okay, water is 1000 kilogram per meter cube. Okay, so this is the formula. Specific gravity equals to density of a material or the fluid divided by density of water at 4 degrees Celsius for the water. Okay, so we can see the table here. So some of the specific gravity at 0 degree. So water 1.0. Why 1.0? Why water 1.0?
Because water over water is
Yeah. So the density of water is 1000. 1000 divided by 1000. So you get 1. Okay. So blood 1.05. Is blood thick, the density is higher or lower? If 1.05 higher. Okay, so because here will be 1005 divided by 1000, so you will get 1.05. So sea water density is higher, so that's why compared to the normal fresh water, you can tend to float a bit in the sea. Okay, gasoline density is lower, 0.7. So ethyl alcohol 0.79, mercury 13.6, okay, wood 0.3 to 0.9, gold 19.2, okay, bone 1.7 to 2, ice 0.92, air is 0.0013. Okay, so from this chart you can see, so which one is, so normally the thing that will be floating, so like wood, okay, gasoline, okay, bones. So bones, I don't know whether you tried before. So ice. So all will be floating in your cup, okay, in the river. So because the density is lower. Okay. Okay, then we know, we have studied about this normal stress. Okay, so normal stress and shear stress. So there are 2 types of stress. Okay, so normal stress is, okay, so let's say this is a surface and you are having an area. Okay, you can have 2 types of force. One coming out of the paper. So let's say you have a surface. So this is a normal. So this is tangential. Okay, so we have normal to the surface, we call it as a normal stress, and tangential to the surface we call as a tangential stress or shear stress. Okay, so we have two. Okay, the formula will be, we know formula for stress is force over area. For normal stress, so you take normal force, okay, normal force divided by area. Shear stress is tangential force divided by area. So there are two types. Okay, so stress is recalled as force per unit area and is determined by dividing the force by the area upon which it acts. Okay, so stress, so this is the formula for stress. Okay, force over area. So that's why I think if you still remember, so why we always say we are having stress? Because constantly something is eating at the same point, so your brain. Okay, so you are saying I am having stress. So you are not saying I am having force. I am having tension. Tension maybe lah. So tension is a type of force, right? So when constantly some force is acting in the same area constantly, we call it as a stress. Okay, normal stress is defined as the normal component of the force. Okay, so previously we have seen, so let's say this is the force acting on the area, we can divide it. So if you, I think it's a basic mathematics, right? So we can have two components, one is tangential and one is normal. Okay, so normal stress is acting, we are considering the normal component of the force. Okay, so this is the repetition from the previous slide. So normal stress is normal force divided by the area, and shear stress is the tangential component of the force. Okay, shear stress, shear force divided by the area. Okay, so if the question is asking you specifically to calculate shear stress or normal stress, so you need to use the formula correctly. Okay, so you can see, so let's say you have two plates, okay, two plates, and you have a rubber in between, and only the top plate is moving, so down is stationary. So what will happen to the rubber? So the rubber will start to deform. They start to deform in the direction of the force. So from here we can calculate the shear stress because it is tangential. Okay, then velocity. So velocity is another important property of fluid. Okay, so you can see, so similar. So you have two plates. So the top plate is moving, and when the force is applied, so the plate will move with certain velocity. Okay, and we know that the bottom plate is not moving, is stationary. So we can have a velocity profile, okay, for the fluid inside. So the fluid which is attached to the stationary body will not move much. The velocity will be small. So that's why you see the arrow on top is longer, because more velocity. So as it goes near to the stationary part, so it will have a smaller velocity, and at one point the velocity will be 0 at the contact point. Okay, so from here we can create a velocity profile. Okay, so velocity is defined as the ratio of displacement over time. Okay, so because meter per second, so in 1 second how many meters it can travel. Okay, so we can so if it's centimeter, then you can convert it. Okay, so viscous, so this is the same thing. Then we move to the viscosity. So another parameter that we can see is viscosity. But under that we have another two new thing. We call it as a dynamic viscosity or absolute viscosity. So this is the symbol for viscosity, mu. Okay, viscosity expressing the magnitude of the internal friction in the fluid, because when you have a fluid, so let's say in a pipe, so you will have internal friction inside. Okay, so viscosity will determine the magnitude of the internal friction, okay, as measured by the force per unit area resisting uniform flow. Okay, so when you have a flow of water inside the pipe, you can have a friction inside, and the friction will try to slow down the flow. Okay, so that is what we call as a viscosity. So viscosity, the formula is viscosity mu, okay, divided by shear stress, okay, or the tangential stress, divided by velocity gradient. So we call it as a du over dy. Okay, so you can see here. So what is du over dy? So that is the rate of deformation. Okay, rate of deformation. Okay, so you can see water, oil and air. So we can see some comparison. So the slope is the viscosity. Okay, so A over B. Okay, so mu equals to R over du over dy, or you can take the component of A divided by B. Okay, so you can find the viscosity of the material. Okay, so I think you still remember. So Newtonian fluid and also non-Newtonian fluid. Okay, so we have studied in chapter 2. Okay, Newtonian fluid. So we can use the same graph. Okay, shear stress over rate of deformation. So if it starts from 0 and it is a straight line, so we call it as a Newtonian fluid. So if it starts from 0 but it is not a straight line like this or like this, we call it as a non-Newtonian fluid. Okay, so meaning other types of fluid, so like Bingham plastic, pseudoplastic, dilatant, so all these are considered as a non-Newtonian fluid. Okay, like toothpaste. Okay, so all are considered as a non-Newtonian fluid. Okay, so kinematic viscosity. So kinematic viscosity is the ratio of dynamic viscosity to density. Okay, let's say the question is asking you to calculate the kinematic viscosity, then you can use this formula. Okay, so dynamic viscosity mu over density. Okay, so after this chapter finish, we will have some questions that we will try to apply all this formula. Okay, for now you just need to know what are the things, what are the formula available, what are the properties available. Okay, so if I can do after this chapter, then I will do. If not, we will do at the in the exam clinic before the exam. So you will have like a tutorial, okay, for you to prepare for your exam. Okay. So both dynamic viscosity and kinematic viscosity of a fluid depends on both temperature and pressure, although the dependence on pressure is rather weak. Okay, so the viscosity is depending on the temperature mostly, but pressure maybe a little. So that's why we have a car. We always will have engine oil, we'll have brake oil. So after some time, so we need to change. Why we need to change? Because it is exposed to temperature, the vehicle temperature, the environmental temperature. So the viscosity will become not viscous. So it will become diluted over time. So we need to constantly do servicing to the car. So we change the new oil, then you can see the performance of the car will be good. Maybe after some time, so you need to change again. Okay, maybe 3 months, 6 months. So that's why, that is because of this. Because the viscosity is depending on the temperature. So maybe pressure inside. So now usually the pressure inside a system will be uniform. So unless there are some external factors which influence the pressure, but the dependence on the pressure is rather weak. Okay, for liquids, both dynamic viscosity and kinematic viscosity are practically independent to pressure. Okay, so it's not really in the car, it is not really depending on the pressure, and any small variation of pressure is usually disregarded. Okay, that's why we don't have a pressure meter in the dashboard. Okay, so any car have, so normally we will use any indication of eye pressure. So any car, maybe Continental car will have, okay, so some indication, but normal car we don't have an indication that, so there's a high pressure in the engine oil, so no. So because so small variation of pressure is usually disregarded. So disregarded meaning is negligible, so we're not taking into consideration, except in extremely high pressure. So let's say you are working in an extremely high pressure environment, so the vehicle is exposed to high pressure, then maybe we will take into consideration. Because if too high pressure, so suddenly the fluid become too high pressure, explosion can happen. Okay, a lot of hazard can happen. Okay, so that's for liquid. For gas, this is also the same case for dynamic viscosity at low or moderate pressure, but not for kinematic viscosity, since the density of a gas is proportional to its pressure. Okay, so the density of gas will be a bit different from liquid, because the density of gas is proportional to the pressure, meaning if the density increase, the pressure will also increase. Okay, so you can see the example here. Okay, air at 20 degrees Celsius and 1 atmospheric pressure. So the mu is 1.83 times 10 to the power of negative 5. Okay, so this is your kinematic viscosity. Okay, 1.52 times 10 to the power of negative 5. So air at 20 degrees Celsius, and you increase the atmospheric pressure by 4 times. So increase to 4 atmospheric pressure. So you can see the mu equals to 1.83. It is still the same like this, but the kinematic viscosity reduces. Why it reduces, not increasing? Why? Okay, based on this, why it reduces? So because the statement says density of the gas is proportional to the pressure. Yeah. Okay. Hello. Sorry. Okay. So V, sorry, it's not V, so this is different kind of V over rho. So this is the equation saying, so if rho is proportional to pressure. Okay, so we know that when you increase the pressure, so if you increase the pressure, your density also increase. So if the density increase, so kinematic viscosity will reduce. Okay, so this is based on the equation. So if the pressure increase, your density will increase. So if the density increase, your kinematic viscosity will reduce. So that's why the value here is reduced. Okay, so if you want to know why it reduced, it's because of this condition. Okay, so that's another case, we call it as a no slip condition. Okay, no slip condition. So consider the flow of a fluid in a stationary pipe or over a solid surface that is non-porous. Okay, so if you want to recall, so So this is solid. Solid is something that really have stuff inside, and porous, so there are a lot of air gaps in between, okay, like the sponge. Okay, so we can consider, so let's say you have a uniform approach of velocity. After some time, when you reach the plate, so you can see it will be like this. So on top, which is not attached to the plate, it will be moving freely, and the one that attached to the plate, so the velocity will reduce because of friction. Okay, we have a friction here. Fluid in motion come to a complete stop at the surface. So at this point, so zero velocity at the surface, because the velocity, the fluid is touching to the surface. So we call it as a zero velocity point or no slip condition. Okay, so the fluid in direct contact with the solid stick to the surface, and there is no slip. This is known as a no slip condition. Okay, so if in the exam I ask, please explain no slip condition, then you can explain all this. Okay, so a point where there will be a zero velocity because the fluid is touching to the surface. So you can explain. The no slip condition is responsible for the development of the velocity profile. So earlier we have seen the velocity profile, okay, in the previous slides. So velocity profile. So this velocity profile is happening because of no slip condition. Okay, so you can see, so you have a solid body here, and you have a fluid flowing. So boundary layer is a flow region adjacent to the wall. So you have a wall, and you have a boundary, okay, which is a viscous effect. Viscous we will study later. What is viscous? So so we can see. So we can see there will be a point where the no slip condition will happen. After some time, we can see there will be a separation point. So where the fluid will start to take over. Okay, start to take over. So separation point is the location where the boundary layer may no longer remain attached to the surface. Okay, earlier it was attached to the surface because of no slip condition. After some time, it will reach to a point where it cannot really stop. So it need to move. Then the separation will happen at the separation point. Okay, so separation point, I think easy to understand, because that's the place where the separation will happen and the fluid will start to resume back at the constant velocity. Okay, so the boundary layer may no longer remain attached to the surface and separate from the surface. Okay, so like this. So it will separate and it will start to move. Okay, so classification of fluid. Fluid mechanics is defined, okay, as the science that deals with the behavior of fluid at rest. Okay, so there are two types of fluid that we are going to investigate. One is static fluid. Okay, static fluid meaning the fluid at rest. So meaning it's not moving, like in a pond, swimming pool. Okay, so we will study what are the things that are related to the fluid at rest or static fluid. And the fluid at motion, we call it as a dynamic fluid. Okay, so dynamic because it's moving, like river. So what else? Pipe. Okay, pipe flow. So a lot of things that the fluid is moving, we will also study on that. Okay, so there is a wide variety of fluid flow problem encountered in practice, and it is usually convenient to classify them on the basis of some common characteristic to make it feasible to study them in group. Okay, so in our daily life, engineers, so you all as an engineer will face, so let's say you are going to industry, so you will be dealing with oil, you will be dealing with water, steam, so a lot of fluid, okay, whether it's in a liquid form or gas form. So you need to understand, so you need to know, okay, so this one, this case, this is a static fluid, so this case is related to dynamic fluid. So based on your analysis, then it will be easier for you to study them and come up with a solution. Okay, so it is very important. Okay, so viscous versus inviscid region of flow. So there are two types of region. Okay, viscous flow is the flow in which the frictional effect are significant. Okay, like earlier the no slip condition. So we can see the frictional effect is very significant because it can stop the flow at one point. So we know that is a viscous flow. Inviscid flow is the region where the viscous forces are negligibly small compared to inertial and pressure force. Okay, because we know in a pipe, so let's say in a pipe, so constantly you will have water going in. Okay, so it will create the pressure force because the water is moving by pressure. Okay, but at one point, so you can have a no slip condition, but after some time it will move, it will become an inviscid flow because the no slip condition cannot really stop the water at one point. Okay, so you can see some example. So at the separation point, so you can see, so this is a no slip condition. Then after some time, so the pressure, the velocity will become constant. So the bottom part we call it as a viscous. Okay, so viscous meaning the frictional effect is significant because here it can stop the velocity of the flow. So we consider this part, the bottom part, as viscous, and the top part, so is not really affected by the friction. Okay, no slip condition, so we call it as a inviscid flow. The inviscid flow meaning is not subjected to friction. Okay, so internal versus external flow. Okay, so I think from the name you know, so internal flow and external flow. So a fluid flow is classified by being internal or external depending on whether the fluid flow is in a confined space or over a surface. Okay, so external flow is the flow of an unbounded fluid over a surface such as plate, wire or pipe. Okay, so external flow, so meaning it is happening outside the surface. Okay, like drain, so we can see drain, so it's not in a pipe. Okay, it's normally one part will be a surface, so it will help to contain the water, so another part will be exposed, so we call it as an external flow. Okay, it's unbounded fluid over a surface. Okay, internal flow is the flow in a pipe or duct. Okay, there are two types, two things, pipe and duct. We always, both also we will call pipe. Okay, so because that's our common practice, but there are different between pipe and duct. So fluid is completely bounded by a solid surface. So if everything is covered and the fluid is moving inside, we call it as a internal flow, especially like a pipe that we are using in a house. So the water is not on the surface, right? It's moving inside, right? So we call it as a internal flow. The flow of liquid in a duct is called open channel flow if the duct is only partially filled with the liquid and there is a free surface. So let's say you have a pipe. So let's say you have a pipe. So let's say a bigger pipe. Okay, maybe like the underground. So under the road. So normally you left. So if you watch Ninja Turtle, so you will go inside So they still can breathe, right? Because only small portion will be covered with water. So the remaining will be open space. So the turtle can survive inside. So similar. So it's partially filled with liquid and there are free space. So then we are not calling it as a pipe anymore. We call it as a duct. Okay. So duct can be underground or even on top. So let's say you are having a kitchen. So food court, you always can see the duct. So let's say you are having the wood in the kitchen to suck the excessive of the cooking gas or smoke. So that is what we call as a duct, because one portion will be covered with fluid, another will be open space. Okay, so flow can be internal or external, and internal can be divided into pipe flow and open channel flow. So duct also called as open channel flow. Okay, so there are two names. Okay, so internal flows are dominated by the influence of viscosity throughout the flow field. Why the internal flow is influence of viscosity? Yeah. Okay, so maybe pressure can be a factor, but it's not the main factor. So why internal flow influence of viscosity? So maybe try to think. If you cannot answer, I ask in exam. Friction, yeah, because it's covered. All the area, all the sides having a surface, solid surface. So it will be subjected to friction. So it will be hard to move. Even we want to move inside a pipe also very hard, right? So because our body will be having friction. So similar. In external flow, the viscous effect are limited to boundary layers near solid surface and to weak region downstream the body. Okay, so external flow, we will have an open space, so it will be lesser subjected to friction. Okay, then we have compressible versus incompressible flow. Okay, compressible and incompressible, I think from the name you know. So whether you can compress the fluid or not. Okay, fluid we are dealing with two, either liquid or gas. So normally gas we can compress. We can compress because the molecules will be far, so you can compress, make it near. But liquid, generally it will be incompressible. So water you cannot compress a lot. Okay, so you cannot compress a lot. Okay, so flow is classified as being compressible or incompressible depending on the level of variation of density during flow. So incompressibility is an approximation in which the flow is said to be incompressible if the density remain nearly constant throughout. Okay, so if the fluid is moving from point A to point B, and throughout that point, so the density is remain the same. So we call it as a incompressible. Even though you apply force, it still remain the same. So we know that it is incompressible fluid. So the density of liquid are essentially constant, and thus the flow of liquids is typically incompressible. Okay, because the density is remain the same throughout the journey. Okay, gases on the other hand are highly compressible. So like I say, because of the molecule distribution, so you can compress the gas easily. When involved high speed gas flow, the flow speed is often expressed in terms of a dimensionless Mach number. Okay, so how many of you have heard about this number? Okay, 3 Mach, 4 Mach. Okay, the flight speed. Okay, so like you play a video game, so you're flying a fighter jet, so you will receive a command from the command center to travel at 4 Mach, 5 Mach. Okay, so what is this Mach? So Mach number, or we write as a MA, is speed of flow. Okay, speed of the vehicle or the fluid is flowing, divide by speed of sound. Okay, speed of sound we always will write as c, smaller c. Okay, speed of sound we know it is 346 meter per second. Okay, in the room temperature. Okay, so this is the category. Okay, so sonic means, so you are traveling at speed of sound. Okay, 346 meter per second. So we call it as a sonic. Okay, so not the cartoon. Okay, so you also travel at the speed of sound, I think. So if lesser than that, we call it as a subsonic. Okay, subsonic. Normally, no one will bother about this subsonic. Because most of our car, the train, okay, train in Malaysia are not overseas. So maybe in the bullet train, so traveling more than sonic. But the normal train, our ETS is under 40 kilometer per hour. Okay, but if you convert to meter per second, then you can see it's still under subsonic category. Sonic maybe the Ferrari car, okay, Formula 1 car. So maybe it's traveling near to the speed of sound. Supersonic is above. Okay, so it's above, but it's not reaching 2. So we call it as supersonic. And above that, the fighter jets, or even some of our commercial plane will travel at the hypersonic. Okay, so it will be traveling at a very high speed. Okay, gas flows can often be approximated as incompressible if the density changes are under 5%, which is usually the case when Mach lesser than 0.3. So this for the gas flow is incompressible if the changes of density is less than 5%. Okay, so over a certain distance, if the changes in density is not changing much, less than 5%, then we call it as incompressible. Incompressibility effect of air at room temperature can be neglected at speed under about 100 meter per second. So let's say you are doing some analysis and the analysis is lesser than 100 meter per second. So then you can neglect the compressibility effect of gas because it won't have much changes. Okay, then we have a laminar versus turbulent flow. Some flows are smooth and orderly while others are rather chaotic. Okay, so laminar flow is highly ordered fluid motion characterized by a smooth layer of fluid. Okay, so and we have a turbulent flow and transitional flow. Okay, so that's the best example for this. So your cigarette. So let's say you have a cigarette. Okay. So anyone smokes. Okay. So let's say how let's say you are blowing the cigarette smoke. So how the flow will be initially? So it will be like this. It will go. After some time, it will right, and you'll have some transition. So this is what we call as a laminar. So it will be straight. So from the direction that you blow, so it will be straight. After some time, because of the gas effect in the environment, it will become unstable. So this we call as a turbulent. Okay, so even in the aircraft, you always will hear the pilot say, so we are experiencing some great turbulence. So so there is some changes in the velocity of the cloud, of the wind. So you will experience very hard time in the flight. Okay, so this is laminar. Laminar normally will be smooth and orderly, and turbulent will be chaotic. So it will be without any proper order. So it will one molecule will go to the left, one molecule will go to the right, so it will not have a proper formation. So the changes between laminar to tubular is what we call as a transitional flow. Yeah? So this place, we call it as a transitional flow. So there are only three things here. Okay, laminar flow, highly ordered; turbulent flow, highly disordered. Okay, and transitional flow is a flow that alternates between being laminar and turbulent. Okay, so transitional. Okay, so natural or unforced versus forced flow. Okay. Okay, so natural or forced flow. The force is the fluid is forced to flow by an external mean, such as pump or fan. Okay, so you need to create a flow using a device. So let's say a pump in your house. So let's say the water flow, the water pressure is low. So you on your pump, so the flow will increase. So that is a force type of flow, because you are using something to create the flow. Natural flow is by the natural mean. Okay, so it can be because of buoyancy effect. Buoyancy effect, I think you haven't studied. It will be under static fluid. So that's why when you jump into water, after some time you can experience something is pushing you up. That is because of buoyancy force. So that is something that is available by natural. It's not created. And steady versus unsteady flow. Okay, steady is a uniform types of flow, but steady is always related with time. Okay, that's why I always say oh, this man is very steady, because over time he is very conscious. You will be very clear. So if you are saying a person is not steady, meaning he keep on changing. So one time you will be smiling, another time you will be angry. So we know that the person is not steady. So similarly, steady flow implies no changes in property. So it can be velocity, temperature, or etc. over a point of time. So let's say after 5 seconds, still having the same property. After 1 hour, still having the same property. So we call it as a steady flow. So unsteady flow, it will keep on changing. So after 5 seconds, so reduced by 1 meter per second. After that, suddenly the temperature rises. So we know that it is a unsteady flow. So unsteady flow, you need to analyze in fraction. Okay, for point 1 to point 2, this much. So you do the analysis. Then you need to keep on do the analysis, and then you add up. Okay, many engineering devices operate for a long period of time under the same condition, and they are classified as steady flow devices. Okay, so we as an engineer, we come up with solution. So we try to create a solution which is steady. So not like you only do some investigation for this kind of condition, but you are not doing. That's why it's very important when we buy something, we need to read the SOP. We need to read the user manual. So it will always say, so this device we only can use between this temperature to this temperature. So let's say the device only can be used until 80 degrees Celsius. You don't use it under 100 degrees Celsius. Then the device will not perform like how we want. Okay, so that's why it's very important for us to ensure that whatever solution that we come, it's steady over time. So it can be long term. Okay, so the volume, the mass, and the total energy content of a steady flow device or flow section remain constant in steady operation. That I think already explained. So all the properties must be constant, okay, for long term. Okay, 1, 2, or 3 dimensional flow. So it's best characterized by its velocity distribution. Okay, and thus flow is said to be 1, 2 or 3 dimensional if the flow velocity varies in 1, 2 or 3 primary dimension. Okay, meaning we know that let's say velocity. So velocity is moving in one direction, and 2 direction normally we can imagine, but 3 dimension, so it will be in various angle. So various angle. So we need to determine so whether it's a one dimensional problem or 2 dimensional problem or 3 dimensional problem. Okay. So the variation of velocity in certain direction can be small and can be ignored with a negligible error. In such cases, the flow can be modeled conveniently as being 1 or 2 dimensional, which is easier to analyze. So if we want to analyze, so don't try to analyze a 3D model of a problem. So it's very hard for us to imagine. Okay, so try to make it a 1 or 2 dimensional. So you can calculate it easier. Okay, so I think that's all for today. So viscosity we will cover tomorrow. Okay. Okay, so it's off.